I'm Mike Jacka. I'm a geotech engineer at Tonkin and Taylor. Earthquake geotech engineering is sort of my thing. And like reflecting back on what Amy was saying there about complexity, I was thinking about some of the projects I've done over my career and where they sort of compare to this. Are you guys seeing that full screen now? The sort of white background? Cool. So these are jobs I've worked on that I think are sort of similar in complexity in terms of the foundations for strengthening. There's the Auckland War Memorial Museum in Auckland. We could dig out underneath that. There's Wellington Town Hall, where we had to dig, in some cases, below sea level to underpin that one. Christchurch Town Hall, sort of complicated a bit by the fact it was earthquake damaged by the time we came to try and fix it up. And the Canterbury Museum here in Christchurch, which we're currently working on, and that's an underpinning of a 150-year-old building. So sort of as I see it, this Rotorua Museum project is of a similar level of complexity to these other jobs that we've had over the years. So this is sort of the top end of where you get to with earthquake strengthening the foundations. While those projects were complicated, there is one thing here which is more complicated, and that's these ground conditions. So all those other projects I showed you were on pretty conventional ground. Here we've got this geothermal issue that gives us problems both in terms of getting the testing done safely, getting the results out of that. The analysis techniques we use around the rest of the country are sort of fall a little bit short when you're in these strange sort of soils, and it gives you some issues for construction as well. So all of that makes this, as well as being a complex building, a really complex site. And so that's why we're here. This is the sort of stuff that we specialise in. And particularly, I think with these public buildings, it's really important to give your communities confidence in what you've got. I know for the Christchurch Town Hall, we had a minister walking around calling it an old dung, it should be knocked down. I think it's important we instill confidence in our public in these buildings. So if we think about testing, how we normally do testing is a very high-tech method where we get a big truck and we push a sharp rod into the ground. And that works really, really well for most places around the country. It gives us good information about the soil strength. The problem at this site is that our soil looks like this. These pumiceous soils. So this is zoomed in 45, 200 times, and you'll see it's not really soil and sand like we know it. It's more like a weak honeycomb sort of structure. And so as soon as we start pushing our equipment into this material, all we do is crush those grains. So we can't actually use the tools we normally use to measure the strength of the ground. And so in those initial stages, we did the best we could with the conventional approach, and we got through to a solution. It was looking like 40% NBS was about where you're going to land until you got liquefaction kicking off, so to cause some consequences for your building. And here's why. When we draw that stuff out of the ground, you can see this material just falls apart. This is when it's come straight off the drill rig. By the time we get that back to the office, it's gone to complete soup. So it just liquefies in the car on the way back to the office. And so you have to assume that this material is liquefiable based on that. That's okay. For liquefiable ground, we've got lots of solutions that we use underneath existing buildings that are suited to this kind of stuff. Here's some other examples that we've worked on around the country. PwC building in Wellington Waterfront, it's got a cellular grid of this jet grout improvement where you drill down under the building, mix it with cement, form these columns, link it all together. You've got a good strong foundation. So we've used that under Christchurch Town Hall, you'll see here. We used it under the Christchurch Art Gallery here. There's an example here. This is Elizabeth Towers in Tauranga, which is under construction at the moment. This is the Bay Link in Tauranga as well. And you'll see in here, here's this grid structure that we're installing. So we've got a really rock solid option that we can use to take care of liquefaction. And so when we were setting it at sort of 40% NBS, these are the kind of techniques you go to fix it. The problem is, as you can probably tell from the scale of those buildings, it's an expensive approach. It's good, but certainly you pay for what you get, which is where Plan B came in. And that was to look really carefully at, is it really 40% NBS that this stuff liquefies? And so we went and used some pretty flash techniques that they've come out of Japan. We've been developing them since the Canterbury Earthquakes in conjunction with the universities. And it's a way of doing really high quality undisturbed soil sampling. And so you see over here, this is the sort of sample we can get back now, rather than that jumbled mess in the box. That means we can stick into this machine here. It may well look like a 1960s power plant, but this is actually one of the top triaxial testing machines in the world. It was just smuggled out of Japan by the professor at the university here when he came across. So this is top-notch research grade testing equipment that was able to test a sample like this and give us some good results. And so what we do then is we actually load that sample like an earthquake would. We give it a cyclic loading. So rather than just sticking a rod into the ground, we are physically shaking that soil. And when we look at this test data, that shows us that actually we can get to about 70% NBS before we start to have any issues with liquefaction kicking in. So a substantial improvement in the goalposts, if you like. That option was put to the project team. Is 70% okay rather than the 80% you're asking for, at a substantial reduction in the cost, but still getting the performance that substantially improved. And so that's where we've landed. That then leaves us with options that are much more surgical, if you like. So rather than that big grid of concrete underneath the whole building, we can start targeting areas of the building where we really need to provide extra support, like under the heavy walls. With things like these small micro piles, or we can use jet grout targeted in specific locations as well. So that's a substantial saving. I'd pick many tenfold saving in the costs of these groundworks compared to the original approach. So certainly it's taken a fair bit of time to get this testing done. But I mean, I use this project as a success story around the office and around, when I'm talking around industry, about how investing in high quality testing to understand the ground can save you a lot of time and angst and money in the long run by getting a better understanding. So I'll leave it there, but thanks for that.